Okay, this is a quick explanation of how to perform an experiment to prove, or two experiments to prove Newton's second law, F is equal to ma. So you can imagine to start with that you've got these three guys and they're going to give the trolleys a shove. During that shove, which trolley would experience the greatest acceleration? And I hope you'd recognise that the Photoshop man here would be the person who'd have the greatest acceleration, the trolley that would have the greatest acceleration. So let's apply this to an experimental situation. Here we've got a trolley with some masses on it. It's a 900 gram trolley and it's got a couple of 100 gram masses, which if you convert to weight on Earth is about 1 Newton. And the idea is that you use a trolley, this is all the mass in the system is everything. This 100 gram, this 100 gram, this 100 gram, and that 900 grams, that's all the mass. And that's going to be accelerated by the force of 1 Newton, which is hung over this pulley on a piece of string. As long as the 1 Newton is falling, so the distance that it falls will have to be the same as this distance that you're dealing with here, then this object is accelerating. This equation we'll come to later if you want to know where it comes from, but essentially for now just pretend it's like a magic speed gun or acceleration gun that can measure acceleration. So what you can then go ahead and do is allow the weight to fall, pulling the trolley, accelerating it. You know the distance, you can measure the time, plug the numbers into the equation, and you can get a value for acceleration. It's a good idea to repeat the experiment 3 or 4 times, and then you can take one of the masses from the trolley and move it to the weight area where it's going to pull. So it's still the same amount of stuff being accelerated, but now you've got a greater force pulling. And again, repeat the experiment several times and do for a new pulling force for the same amount of mass. So you'll get a set of results which you can explore. So here's like a way of imagining that set of results. Hopefully you can imagine that for a small force you'll get a small acceleration. And what you actually do get is you get a direct relationship between force and acceleration. So that if you plot it on a graph, it becomes a straight line graph. So force is proportional to acceleration if the mass remains constant. And as it turns out, you can imagine that the greater the mass, for the same force, let's say that larger force there, you get much less acceleration. And the steepness of the line is in fact equal to the mass. This is how you could define mass, or how it is defined. So large mass, medium, small mass, and you can see it relates to the gradients. So since gradient is equal to change in y over change in x, on this graph that would be force divided by acceleration, so we could say that mass is equal to force divided by acceleration. So with a little bit of rearranging of the equation, just turning that around, we can multiply both sides by acceleration, cancelling acceleration on this side, and we get to the normal way you would see Newton's second law, F is equal to ma. So that's one way around doing the experiment. Let's look at another way. This time we can keep the pushing force the same. So who do you think would have the best acceleration? Hopefully you can imagine it will be this person with an empty shocking trolley. So this time we keep the force the same and we change the mass. So you can do measure the time, plug number and distance, plug numbers into this formula, get the acceleration, repeat the experiment for a different total mass, including 100 grams from this, and again repeat with a different mass, and you get a different set of results. This time, small mass, so if you make the trolley very, very low in mass, like that, you should get a larger acceleration. Medium mass, the acceleration will go down. Big mass, the acceleration will go even smaller. Okay, so you end up with something that looks like this, which if you do maths, you recognize as an inverse relationship. So acceleration is proportional to 1 over the mass. So in order to make this easier, it's a nice neat trick you can do in maths and in physics, is you can divide mass into 1, sorry. So a small number going into 1 gives you a big number. A medium number fitting into 1 gives you a small number, and a very large number going into 1 gives you a very small number. So now we can think about plotting 1 over mass against acceleration. This is nice because it means you can draw a line of best fit, you can measure a gradient, which are all pretty straightforward things to do in maths. Okay, so we've plotted 1 over mass and acceleration. And this time round, what you find is that the force is actually the gradient, and I can show you why. If you're dividing acceleration by 1 over mass, and we're saying it's going to be equal to force, when you're dividing by 1 over something, right? So think about it with numbers. If you have 1 divided by a half, the answer is actually 2. It's the same as saying 1 times 2, right? So you can speak to your math teacher if you want to understand the way this works, but essentially we can invert 1 over mass and multiply it by acceleration, and you end up with force is equal to mass times acceleration. So it's quite neat. You can get to the same conclusion by different methodologies, so it's concordant, or it's a concordant set of ideas. They all fit together nicely. Okay, so we're back to F is equal to ma. Right, so this is pretty much the end of the presentation, unless you want to know where the formula for acceleration came from, or you want to know some practical considerations when doing the experiment. Okay, so let's have a look at some practical issues setting up the experiment. Right, so the first thing is that you want to try and make the event take as long as possible, right? Because if you're timing by hand, every time you press start and stop the stopwatch, you're adding plus or minus 0.1 seconds, and if you can make the time period for which the event takes place longer, then your percentage error becomes smaller, so that's an advantage. So making the wait fall further, so D is longer, means the event takes longer. That's something you can do. Use very small masses, or weights basically, to accelerate this object. Will also make the event take longer and reduce error. Similarly, you can increase the mass of the trolley itself, right? So, or you can use timing gates as well, right? So all those things can increase the accuracy with which you perform the experiment. You can also try and compensate for the rolling resistance. If you get the trolley and give it a shove, if there was no friction whatsoever, the object would just continue doing what it's doing, right? So its velocity would stay constant, it wouldn't change. If you do that, it won't stay constant. It will slow down. So what you can do is you can place this on a board, this whole thing on a board, raise this end. Oh dear, children arguing. Raise this end and give the trolley a shove, and when the trolley just rolls at a constant velocity, then your setup is compensating for friction, right? So that's something else you could do. I'm sure there's lots of other things you could do. Maybe you could get the lightest, lowest mass wheels, because actually it takes some energy to increase the speed of the wheels, but pretty much that's negligible and could be ignored if the wheels are light. Right, finally let's have a look at where this equation comes from. Okay, so we can imagine that the object just accelerated, and if we assume that the acceleration was uniform, we might just think, oh well, all I need to do is to change velocity over time. Unfortunately, we weren't able to measure change in velocity, we were able to measure just distance and time. So we need to think of a way where we can replace change in velocity with the same thing but expressed in terms of distance and time. So one thing to think about is that the change in velocity will be, we can certainly know the average velocity basically, because we know that we could think of the total distance divided by time. So since average velocity would be equal to total distance divided by time, which this is another way of looking at average velocity, right? The average velocity would be this area divided by the time, or it could be also thought of as this area divided by the time. And you can show geometrically that basically you're taking a rectangle and you can either cut it in half that way or you can cut it in half that way. If you're cutting it in half this way, then the average velocity will be exactly half the final velocity. Right? So if you take average velocity, which should just be d over t, and multiply it by 2, it's going to be the same as final velocity, which means I can sub that equation, or that term, in for delta v. Right? So you get to this. Okay, so this is a bit awkward, but basically you can think of it as 2d divided by t multiplied by 1 over t, which is a tidier way of expressing that, and then you just end up with 2d over t squared. So that's the equation we use. Okay, I hope you found this useful. Thanks for watching.